Alright, from now on, we are going to study some linear algebra, which is basically the study of vectors and matrices. Okay, so let's define vectors. What is a vector? Usually, we visualize vector as an arrow. One vector is an arrow in a space, but we usually don't care about where this vector is located. Okay, so this vector, for example, starts from here, which is called source or tail, and ends here, which is called target or head. So at least we do need 2 points here and here, one for source and one for target. Then we draw an arrow. So this vector starts from this point and ends at this point. So, but what we care about vectors is its magnitude, that is its length, and its orientation, not the place where it is located. So, for example, if we have this vector and we consider this vector as same as this vector where it is located somewhere else. As long as the magnitude, their length, and the direction are the same, we consider these two vectors as equivalent. But what do we mean by equivalent vectors, equivalent arrows? So that's the question. So, we said equivalent, so it is natural to introduce some equivalence relationship. In case of two-dimensional space where we have x-axis and y-axis, so x-axis and y-axis, we need to specify two real numbers to specify 1 point. So this is x s, y s. Let's say this is xt, yt. Okay. And suppose we have another vector, another arrow, which has the coordinate x, u, y, u at its source, and x, v, y, v at its target. So we introduce a relation between two arrows. Okay. So this is how we do it. We say that let's call this arrow A and this arrow B. Okay, we say arrow A is related to arrow B if the following equations hold. First, xt minus xs. So that is this minus this is equal to this minus this, xv minus xu. And also this minus this, so yt minus ys is equal to this minus this, so yv minus yu. So if these equalities hold, then we say two arrows are related. Okay? Then we show that this relation is an equivalence relation. So remember what equivalence relation is? So first of all, we need to show three things. Okay, first of all, it should be reflexive. So that means each arrow is related to itself. So is this true? So according to our definition of this relation, then if this arrow A has these two coordinates in two dimension, then we should have xt minus x xs equal to, so it's the same vector, so it's trivially equal. So yt minus ys is equal to yt minus ys. So it is reflexive. And second, symmetric. Symmetric. So that means if A is related to B, then B is related to A. And if you look at this, if A is related to B, we have this. But this equality is just an equality between two real numbers. So we can swap the left-hand side and right-hand side. So that gives you this relation. B is related to A. So therefore, this relation is symmetric. Okay. And lastly, the last thing we need to show is transitivity. So this relation should be transitive. So that means if A is related to B and B is related to C, okay, then A is related to C. Okay. So let's say we have another vector, another arrow that is related to B. So A is related to B and B is related to C. Let's say this coordinate of the source is xp and yp and xq and yq. Okay, so from this A related to B, we have x t minus x s and x v minus x u, and same for the y coordinate. And from B related to C, we have xv minus xu is equal to xq minus xp, and same for the y coordinate. So from these two equations, xt minus xs is equal to xv minus xu, which is equal to xq minus xp. Therefore, of course, xt minus xs is equal to xq minus xp. Therefore, this means and of course the same is true for the y coordinate, so A is related to C. Therefore, this relation between arrows is an equivalence relation. Now let's consider set arrow. This is a set. So this is a set of all arrows in two dimension. So to specify one arrow in two dimension, we need to specify four numbers: xy for the source and xy for the target. So this arrow is actually this. So this is two-dimensional space for the source and two-dimensional space for the target, which is four real numbers. Okay, tuple of four real numbers. So arrow is actually this set. So if we introduce this equivalence relation, then we can define maybe just write arrow we can define the equivalence classes induced by this relation, which gives us this quotient set of arrows, and that is actually isomorphic to R2, because this relation means if we can move if we move all these arrows, equivalent arrows, to here, so the source of the arrow coincides with the origin, and so all equivalent arrows. Oh, wait a minute. Well, anyway, if you move this arrow to this point, so the source is at the origin, all the arrows, equivalent arrows, will be identical. So that means to consider the set of equivalent arrows, we need to specify only two real numbers. That is the coordinate of the target, because the source is fixed at the origin. So far we have considered only two dimensions, but the same argument can be applied to any dimensions. So in the case of three dimensions, we need to specify 6 real numbers to specify one arrow. But by introducing equivalence relation in a similar manner, uh, uh, this quotient set will be reduced to 3 dimensions. And in the case of 4 dimensions, we need to specify 8 real numbers. So that is actually 8-dimensional space. But if we introduce this quotient set, then that will be just 4-dimensional space, and so on. So in general, if we want to consider arrows in n-dimensional space, the vectors are considered as an element of n-dimensional space. Okay, and let's define a row vector, n-dimensional row vector, which is an ordered set of n real numbers. Okay, so this is called row vector because it is n numbers are arranged in a row. And we can define some operations among vectors. First of all, we define addition. Okay, addition between two row vectors. So let's see, if we have x1, x2, and xn, then we have another vector, y1, y2, and yn. Then this addition is between two vectors is defined to be this: x1 plus y1, x2 plus y2, and so on. xn plus sorry, this is yn. So that means we add each element by element. Okay, so this is the addition between two vectors, and we can also define multiplication by a real number. Okay, let's say this lambda is a real number. Then we define the multiplication between a real number and a vector as this. So lambda x1, lambda x2, and so on, and lambda xn. Okay, and so far we don't define multiplication between two vectors. We only define multiplication between one real number and a vector. Okay. In this context, this real number is called a scalar, as opposed to a vector. Okay. So scalar is not a vector. It's called scalar because it scales each element by this constant. Okay. And we can also arrange these n numbers in vertically. So we can write x1, x2, and so on in this way. And this is called a column vector. Okay, so this is, well, information-wise, this has the same information as the row vector, but distinguishing between row vectors and column vectors come handy at some point. Okay, and if this, the number of dimensions, so this n, if this n is not prime, then we can arrange in a more different ways. For example, if we have 6 dimensions, 6 is a multiple of 2 times 3. So we can arrange in these ways. So x1, x2, x3, x4, x5, x6. So this is a row vector. And we can, of course, write x1, x2, and so on up to x6. It's a column vector. And we can also write these numbers in 2 rows and 3 columns. x1, x2, x3, x4, x5, x6. And this is called a 2 by 3 matrix. Okay, and of course we could write x1, x2, x3, x4, x5, x6. So this is 3 by 2 matrix. Okay, so this is 2, this is 3. So this is 3, and this is 2. So the number of rows comes first, 3, 2, or 2, 3. And the number of columns comes next. Okay, this 2, this 2, this 3, and this 2. Now, so far we have only considered vectors or matrices in these forms. So it's real number, set of real numbers, set of n tuple of real numbers. But instead of real numbers, we could use complex numbers. So we could use, these x1, x2 up to x6. They can be complex numbers. Or we could use rational numbers to define vectors and matrices. In fact, as long as we have a field, these real numbers, complex numbers, and rational numbers, they are all fields. So let's say we have some field K. Then we can define a vector space based on this field. Okay, so there can be some other fields, right? Other than real numbers or complex numbers or rational numbers. But whatever the field is, we can define vectors based on that field. So this set is called a vector space over K. So this can be real numbers, complex numbers, rational numbers, or whatever, as long as it is a field. Of course, when we say vector space, it is not just an arrangement of numbers in these ways, row vectors or column vectors, but we need to also define addition between two vectors and multiplication between scalars and a vector. So scalars come from this field. Okay, scalars are elements of this field K, and vectors are uh, uh, either row vector or column vector. Okay, then we let's define an important notion called linear combination. So let's say V1, V2, V3, and so on, Vn are vectors, either row vectors or column vector, but not mixture of these. If we have row vectors, we only have row vectors here. So it's not mixture of row vectors and column vectors. And also lambda 1, lambda 2, lambda 3, and so on, up to lambda n, they are scalars. So unless otherwise stated, we only consider vectors of real numbers. Okay, something like this. And okay, by the way, this n does not mean the dimensionality of vectors. So maybe we could use a different letter for this. Then expression of this form, lambda 1 v1 plus lambda 2 v2 plus lambda 3 v3 and so on up to lambda n vn. So the expression of this form is called the linear combination of these n vectors with coefficients lambda 1, lambda 2, and so on. Now let me explain some algebraic properties of vectors. First of all, we usually deal with real vector space, vectors with real elements, not complex elements or rational elements, but real elements. But to be general, let's say we have a field. Well, in this case, this is real number, and we let V, this capital V, to represent the vector space. Okay, just to be general. So we have already defined the addition between two vectors and multiplication between a scalar and a vector. Okay, so here are the properties of these algebraic operations. First of all, uh, if we have u and v that are vectors, then the addition, the sum of u and v is also a vector. Okay, so this means addition between vectors is a vector addition is closed in this vector space V. Okay, so if we add two vectors, it is still a vector. Okay, so and also u and v, if u and v are vectors, then u plus v is equal to v plus u. So okay, this is closure, and this means addition is commutative. Okay, and so the order of addition doesn't matter. And 3, if we have three vectors u okay, u, v, w, then this we have this associativity. And u plus v plus w. Okay, this is associativity. Okay, this means first we add u and v, then add w. This is equal to first we add v and w, and then we add u. So if remember, this addition between two vectors is defined between two vectors. We didn't define addition between three vectors. So any additions involving more than two vectors must be done one by one. Okay, so we have to pick two vectors. So if we add u and v, then that gives you one vector, another vector. So to that vector we can add another vector. So we're always dealing with two vectors when we add vectors. So this means the order of addition doesn't matter. That's associativity. And fourth, there exists a special element called 0. So 0 vector. So there is a 0 vector, so such that for all vectors, adding 0 vector doesn't change that vector. Okay. So this is called 0 vector. As the name suggests, in terms of row vector representation, this 0 vector is obviously the vector consisting of only zeros. Okay. And next, for any vector, there is a vector called additive inverse in that vector space, such that u plus minus u. So minus u is the additive inverse. If we add these two vectors, we get that 0 vector. Okay. Remember, we didn't define subtraction between two vectors. We only defined addition. And this negative u is the inverse, additive inverse of u. So and we can abbreviate this expression as just u minus u. Okay, but this is a shorthand. This is a shorthand notation for this expression, u plus negative u. Okay, so the subtraction is just a shorthand for addition between one element with its additive inverse. Okay, and in terms of a row vector, if we have something like u1, u2, up to un, then so if we have u, then negative u is negative u1, negative u2, and so on. Okay. And 6. So far we have dealt with only additions. Now consider multiplication with a scalar. So if lambda is a scalar, so remember this K is a field over which the vector space is defined. And if U is a vector, then lambda times U, which is the scalar multiplication of a vector, is also a vector. Okay. So the vector space is closed under multiplication by a scalar. Okay, so this is another closure property. Closure. And 7. If we have a vector u and two scalars, lambda and mu, then lambda plus mu is another scalar, right? Because K is a field, so K is closed under addition. And if you multiply this, then we get lambda u plus mu u. Okay. Be careful. This addition here between lambda and mu is the addition within the field K. And this addition on the right hand side is the addition between two vectors defined in this vector space. Okay, so the meanings are different, although we use the same symbol plus. Okay. And 8. If u and v are vectors and lambda is a scalar, then lambda times u plus v is equal to lambda u plus lambda v. Okay. As we have noted before, u plus v is a vector. So if we multiply that vector with a scalar lambda, then what we get is this. Lambda u is also a vector and lambda v is also a vector. So this is a kind of distributive law of scalar multiplication. And 9, for all vectors, any vector, if we multiply by 1, the vector doesn't change. Remember, this 1 is the the multiplicative identity of the scalar field. Okay. If this K is a real number or complex number or rational number, then this 1 is the ordinary 1 as a number. But in general, this 1 is that multiplicative identity element of the field K. Okay. And 10, this is the last, for all lambda mu, which are scalars, and for all u vector, we have lambda mu times u is lambda times mu u. Okay. Now again, be careful. The multiplication between lambda and mu is a multiplication within the field K. Okay. And this multiplication between mu and u is the scalar multiplication with a vector, of a vector, right? And this multiplication between lambda and mu u is again a multiplication between the scalar lambda and a vector mu u. Okay, this mu u is an element of the vector space, right? So this is this multiplication this multiplication this multiplication is the multiplication between a scalar and the vector. Okay. Now you may notice the similarity between all these rules with the axioms of a field. But the vector space is not a field. For example, we have zero element for this is additive identity in the vector space itself, but we don't have multiplicative identity, something that corresponds to 1 within the vector space. Here we have 1, this one, but it is not a vector, it is a scalar. Okay, so here we have two different, completely different sets, the field K and the vector space V. So it is completely different from fields. Okay. In fact, vector space is a vector space. It is, it has its own properties that is completely different from fields or any other system of numbers, for that sake. And also you should review that all these rules are derived from the definition of the vectors and the vector addition and scalar multiplication. Okay, so these actually theorems, so to speak. However, just forget about vectors as we have defined before and consider two sets, K, some field K and any set V, where we can define addition within V and multiplication between elements of K and elements of V. Okay, and require that all these rules are satisfied. Then we can consider anything that any set that satisfy all these properties to be a vector space. Okay, so this is another way to define vectors. So instead of array of numbers, we just require some set satisfying all these rules to be a vector space. So this is an abstract definition of vectors, and in fact in some fields, and vectors are not just array of numbers. It can be some functions. In physics, in quantum physics, vectors, state of the physical system can be considered as vectors. In quantum physics, that particular vector space is called the Hilbert space. Okay, from now on, we only work with this vector space for some natural number n. Okay, then let us define the modulus or length of a vector. Modulus or length of a vector. So let's say x is a raw vector. So there are n real numbers in this row, and the modulus of this vector is written as this and defined by this. So that's sum of I from 1 to n and xi squared. So that is to be more explicit, it's defined by this. Okay, so this is just a definition. Let's see some easy examples. Let's say if n is 1, so that is one-dimensional vector. So if n is 1, then this vector is just one number, x1. So its modulus is defined as this, square root of x1 squared, which is just the modulus of a real number. Okay, and in case of two dimension, we have two numbers, 1 and x2. So in that case, the modulus is square root of x1 squared plus x2 squared. So this is the same as the distance between this coordinate x1, x2 from the origin. So this length. So if we have this vector, this length is the modulus of this vector. Okay, so we may consider this definition of modulus as an extension of the distance between the head of the vector from the origin in n dimension. Okay, next we define a unit vector. So if x is a vector with modulus 1, then x is said to be a unit vector. Okay, so any vector with length 1 is a unit vector. And another definition, it's called scalar product. Okay, let's say x and y are row vectors. Then we define the scalar product between x and y by this. So x and y, so we enclose by brackets, is defined by this, xi, yi. So that is x1 times y1 plus x2 times y2 plus and so on up to xn times yn. So we take the product of each element, x1 with y1, x2 with y2, and then take the summation of all these elements. So that is called the scalar product between two vectors. Okay. Now here's the now finally we have defined a multiplication between two vectors, but the result is a scalar. Okay, because this is a real number, x1 is a real number, y1 is a real number, so this is a product between two real numbers, and then we add n real numbers, so the result is a real number. Okay, that is to say, the result is a scalar, okay, rather than a vector. The result is not a vector, it's a scalar. So that therefore it is called the scalar product. And this scalar product is also sometimes called inner product. Or dot product. because instead of writing like this, some people prefer to write like x dot y to mean this scalar product, or yet other people might want to write parenthesis x y. Or in physics, in quantum mechanics in particular, people tend to write x bar y bracket. So this is called bracket notation. This part is called bra, and this part is called ket. It's called bracket. But they all mean the same thing. So depending on the context, we may use different notations. Okay, but in any case, the result is a scalar. In this case, it's a real number. Okay. So this scalar product may be considered as a mapping or function from Rn times Rn to R. Okay, so this something to real numbers. Something. Okay, so this is a vector, this is a vector, and this is a scalar. Okay. Now you should see that this scalar product and the length of vectors are closely related to each other. For example, we have this relation. So the scalar product of x with itself is equal to the square of its length. This is easy to see because this right hand side is x1 times x1 plus x2 times x2 and so on, xn times xn. So that is x1 squared plus x2 squared and xn squared, which is the square of the modulus of x by definition. And similarly, you should prove the following. For example, here lambda is a scalar and x is a vector. This modulus is equal to absolute value modulus of lambda times modulus of x. Okay, and the scalar product is commutative. And what else? Okay, x plus y and z is, so this is kind of a distributive law for scalar product and vector addition. And y, z. And of course, since vector scalar product is commutative, we also have this. And here's a result involving two types of products. This is equal to lambda x and y. So notice here, this multiplication, lambda times this scalar product, this is a multiplication between two real numbers because the result of a scalar product is a real number and this lambda is a real number. But here, the multiplication between lambda and x. This is a multiplication between a scalar and a vector. Okay, so these multiplications have different meanings. Okay, and of course we have similar result for the second argument, lambda y. Okay, so this lambda can come either here or here, but not both at the same time. Okay, so don't write like this. X lambda times x y is not lambda x lambda y. Okay, so this is wrong, and you should prove this. Next, we are going to study geometric meaning of scalar products. Okay, here's a proposition. Let u and v be two-dimensional vectors. Okay, then we have this result. U v scalar product is equal to the modulus of u times the modulus of v times cosine theta, where theta is the angle between u and v. So in two dimensions, if we have u and v, let's say, then if the angle between these two vectors is theta, then we have this result. Okay, so let's prove this. First, we consider the case where u and v are both unit vectors. So suppose u and v are unit vectors. Okay, then we can write u as cosine, let's say phi, and sine phi, and v as cosine psi and sine psi, where phi and psi are angles between these vectors with this horizontal axis. So in this case, u has phi as angle, and v has psi angle. Okay. This is possible because u and v are unit vectors, right? So as we have learned in complex numbers, we can express any two-dimensional points or any points on a unit circle in two dimensions as cosine and sine. Okay. Then their dot product is this times this and this times this. So it's cosine phi times cosine psi plus sine phi times sine psi. And using the formula for addition of angles, this is cosine phi minus psi. Okay? But this is equal to theta. You know, the difference between phi and psi is theta. So if you look at this figure, So phi minus psi is actually it's minus theta in this particular figure, but uh, cosine function is an even function, so we can change the sign of the argument. So it's the same thing. So this is same as this. So in either case, it is the difference between two angles, that is theta. So in this case, uh, this equation holds because modulus of u and v are 1. So uh, as long as u and v are unit vectors, this is true. Okay, now consider more general case where, okay, next case, if u and v are not unit vectors. Then let us define define u hat by this u divided by its modulus, and v hat as v divided by its modulus. By the way, we did not define division by scalar, division of a vector by scalar. So what we really mean by this is this. 1 over modulus of u times u. Okay, so this division is a division between 1 and a real number. So this is the division within real numbers. Okay, so then this is a real number, so we can multiply. It's a real number, so it's a scalar, so we can multiply a vector by a scalar, and same for this. Okay, but of course we have to assume u and v are non-zero vectors. Okay, if they are zero, we cannot do this operation. So this theorem is true only if u and v are not zeros. Okay, so if we define these vectors, then u hat and v hat, they are unit vectors. To see this, so this is this, and as we have seen before, this is u modulus times u, but this part is a scalar, so we can get this out, and this is also positive, so this is just out, and u modulus, so they cancel, and the result is 1, and same for v hat. So we can apply the previous result we have got for unit vectors. So okay, and u hat v hat is cosine theta. Okay. Oh, by the way, scaling by a constant does not change the angle, right? So if we have u here, multiplying by a scalar does not change the direction. It only changes the length. Okay, multiplying by something changes the length, not the direction. So it becomes either shorter or longer, but whichever is the case, it doesn't change this angle. Okay, so therefore the angle between these two vectors does not change. So we still have cosine theta as the result, but this one is equal to this u hat and v hat, and we can take these scalars out of out of the scalar product. Oh, wait a minute. It's not hat here. It's just u and v. So we have this equal to cosine theta. So multiplying both sides by modulus of u times modulus of v, we have uv equal to modulus of u times modulus of v times cosine theta. So that's it. In this theorem, we have proved this result in two-dimensional space. And actually, the same equation holds even for three-dimensional space. But what about more general dimensional space, like 4 dimensions, 5 dimensions, 100 dimensions, or million dimensional spaces? So, but in those cases, how do we define this angle? Actually, at this point, we change the argument. We kind of reverse the argument so that we actually define the angle in higher dimensional spaces by this equation. Okay? So this means in higher dimensional spaces, we define the angle between two vectors as this. So we can define the dot product for any dimensional space, and of course we can calculate the modulus of any vectors in any dimensional spaces. So based on this equation, we may be able to define the angle between these two vectors. So this will become the definition of the angle rather than the result of the dot product. Okay, but to do so, we can say this defines the angle, but does this really make sense? Because this is a cosine function, and cosine function is bounded between -1 and +1. Right? So if we cannot guarantee that this quantity on the right hand side, this one, the scalar product divided by the product of moduli of two vectors, if this is not bounded between, if this does not belong to in this interval, then this equation may not make sense, because if this is, for example, if this value is 2, then what's the cosine theta? There's no such theta that can satisfy this equation. So next we want to prove that this quantity on the right hand side is indeed between -1 and 1, and that is actually the result of the famous theorem called the Cauchy-Schwarz inequality. Okay, theorem. Cauchy-Schwarz inequality. By the way, don't say this is Cauchy. This is not Cauchy. This is Cauchy. He is French, so it's a French name. Okay. So we have for any vectors x and y in n-dimensional space, we have this inequality. The scalar product between x and y, and its modulus is less than or equal to the product of their moduli. Okay, so this is the theorem. Now let's prove this. If x is 0 or y is 0, then this is trivial because both sides are 0, right? Scalar product with 0 vector is always 0, and the modulus is 0, so both sides are 0, and this is true. So suppose both are not 0. X is not 0 and y is not 0. Okay, then for any real numbers, lambda, we have this inequality. This should be trivial. Okay, so this lambda is a scalar. For any lambda, this modulus, x plus lambda y is a vector, so its modulus is always non-negative. So its square is also always non-negative. Okay, but this is equal to this scalar product, as we have seen before. And we have distributive laws for scalar product, so this is, we can distribute this x times x, x times lambda y times x, and lambda y times lambda y. So so after all, we have this lambda squared and y modulus squared, and 2 lambda and x times y and x modulus squared. Okay, so this is this is this. Okay, now consider this, the left hand side, as a quadratic form of lambda. So lambda squared, lambda, and a constant. Okay, so this inequality means that lambda, uh, if we consider this as a quadratic form, then the determinant of this quadratic form must be non-positive, right? So if you plot this function, consider this as a function of lambda, then it's a quadratic function. So, and since this is greater than or equal to 0, it will never cross the lambda axis. So at least, at most, it touches this axis, but it never crosses below this axis. So it is either this, so always above the axis, or it touches the axis at one point, but never this. So this cannot happen. Okay, so this means the determinant of this quadratic form is non-positive. So the determinant is, so 2 times this squared, right? Squared minus 4 this y squared and this x squared. So this is non-positive. So this means x, y squared is less than or equal to x squared times y squared. So from this, we have the desired. So if we take the square root of both sides, we have the desired result. Okay, and that's it. Now, because of this inequality, we can be sure that uh, this dot product between x and y divided by the product of moduli of x and y is less than or equal to 1. Right? So if we divide both sides by this, we have this. So if we get rid of this absolute value, then we have uh, this is between -1 and 1. Therefore, we can define the angle between two vectors x and y by this equation. Okay? Since the right hand side is always between negative and 1, there is some angle theta that uh, the cosine of which is equal to that value. Okay. And now uh, we have defined the angle between two vectors in any dimensional spaces. So 100 dimensions, no problem. Okay. Next proposition. Again, x and y are vectors in n-dimensional space. Then we have this inequality. X plus y is less than or equal to x modulus plus y modulus. Okay, let's prove this. We can use the Cauchy-Schwarz inequality to show this inequality. So first, consider this x plus y modulus squared is this dot product. And this is equal to this squared to xy plus y squared. And for this part, this is less than or equal to its modulus of this scalar product. Okay, then we can use the Cauchy-Schwarz inequality to this part. And 2x times y but this is equal to, if you complete the square, we have x modulus, not square, x modulus plus y modulus squared. So let's take the square root of both sides, this and this. Then we have x plus y less than or equal to x plus y. that's it. As we have discussed before, vectors are actually arrows in space, but their positions in the space are not relevant. But in some cases, it is useful to regard these vectors as points in space. For example, if we have a two-dimensional vector like x1 and x2, and we don't really care where this vector is as an arrow, where this vector is in the space, but if we consider these as the coordinates in two-dimensional space, then this vector is interpreted as a position vector. Okay, and let us see some applications of this interpretation. First of all, let's consider two-dimensional space. And let's see, if two position vectors, A is 1, 2, and B is 3, 4. So we regard these two vectors as positions in space, in two-dimensional space. So let's see. So if we have this coordinate system, A is 1, 2, so 1, 2. So this is A, and B is 3, 4. 1, 2, 1, 2, 3, 1, 2, 3, 4. So now we want to find the equation of the line passing through these 2 points. So let's see, something like this. Okay. So how can we do that? So first of all, the vector, okay, this is A and this is B. Okay, and so the vector from A to B is given by this B minus A. Okay, and in this case, this is 3, 4 minus 1, 2. So that is 2 and 2. Okay, and let's say if we take any point on this line, let's call it R. Okay, R has coordinate x and y. Okay, so what equation does this x and y must satisfy? Okay, so if we take uh, the vector from A to R, then that should be R minus A, and that is x, y minus 1, 2. So that is x minus 1, y minus 2. So if R is any point on this line, it must be it must be a scalar product of this vector AB. Okay, so this is the vector AB, and any point on this line must be a scalar product of AB. So R minus A should be a scalar product of B minus A. Okay. For example, if it is somewhere here, this vector times 2 should be this vector. This vector times negative 1 should be this vector along this line. It's always on this line. So therefore, the equation for this vector should be something like this. So R minus A should be a scalar product of B minus A. Okay, therefore R is a plus lambda b minus a. So this is the general equation for the points on this line. So if r is x and y, then it should be 1 plus 2, so that's a, and plus lambda, and b minus a is 2, 2. So it's 2 lambda plus 1 and 2 lambda plus 2. So that is x is equal to 2 lambda plus 1 and y is equal to 2 lambda plus 2. So, I mean, this is already okay. So any line, any point on this line can be expressed as 2 lambda plus 1 and 2 lambda plus 2, where lambda is some real number. Okay. And if you want to express this equation of the line in terms of only x and y, so we just get rid of this lambda, which can be done by subtracting this from this. So that will give you y minus x equal to, let's see, that's 1. So that is y is equal to x plus 1. So this is the usual expression for the line. But this expression is very intuitive actually. So if lambda is equal to 1, then what happens? So if lambda is equal to 1, then r is equal to a plus b minus a, which is b. So in that case, lambda equal to 1 corresponds to b. Okay. If lambda is equal to 0, then this second term disappears. Then r is equal to a itself. So lambda 0, so lambda 0 corresponds to the point A, and lambda 1 corresponds to point B. And if lambda is between 0 and 1, that's somewhere between A and B. So let's see. So that will be somewhere between A and B. Somewhere here. And if lambda is greater than 1, it's beyond B, somewhere here. Somewhere in this region. If lambda is negative, then it's somewhere here. Okay. Next example. Consider this set. Let's see. So this we now in this case we consider general dimension. So C is a vector in m-dimensional space, and let's define this set P, which is defined by this R. It's a set of points in this space such that this dot product R minus C and C is equal to 0. So what does this mean? This is the set of points that contains point C and is perpendicular to the vector C. So in case of 2-dimension, a plane corresponds to a line actually. So in this case, let's see, in 2-dimension, this would mean, let's say this is point C, for example. Okay, and this set P corresponds to the line that contains C and is perpendicular to this vector. Okay, perpendicular means, let's see, something like this. So it contains this point and perpendicular to this vector. Okay, so this set of points corresponds to this line, this red line. Okay, this is C. Okay, so why is it so? Why does this have this meaning? So consider this dot product. Okay, so any point on this line, let's call it R. Okay, so let's represent R, any point on this line as R, and so C is here, the position vector C. So R minus C means this vector. Let's see, means this vector from C to R. Okay, it's this vector. Okay, and we take the scalar product between this vector and this green vector and this blue vector. And if they are perpendicular, then from the previous theorem, we know that R minus C times C is the modulus of R minus C times modulus of C times cosine theta, where theta is the angle between these two vectors. So that will be, so if C is this way, so the angle is this. So it's right angle. If this is perpendicular, then this angle is like pi half, right? But cosine pi half is 0. So therefore this scalar product is 0. Okay, that's why this set represents this line. Okay. In case of 3 dimensions, it's not so easy to visualize on a sheet of paper, but it's the same thing. So let's see, let's try. So we have 3 axes, and we have some vector C. Okay, so this point represents the vector. So if we have any plane perpendicular to this vector C, then any point R, and take this difference, so this vector represents R minus C. But since this plane is perpendicular to this vector, so we have the right angle. Okay, wherever this R is on this plane, we always have this angle perpendicular to C. Okay, for example, if R is here on this plane, the angle between this vector and this vector is still right angle. So the dot scalar product is always 0. Same is true for higher dimensions, although it's impossible to visualize. The same is true. In 3 dimension, it's indeed a plane, right? So its plane is actually a 2-dimensional subspace of 3-dimensional space. In case of n-dimensional space, then a plane is actually a n-1 sub-dimensional subspace of the n-dimensional space. So in which case we call this plane a hyperplane. it's impossible to visualize, but we can still deal with it using equations. And one more example. Consider again a general point, any point in n-dimensional space. And let's say R is a positive real number. It's a constant. Then we consider this set S. That is the set of points in this space such that the modulus of x minus c is this constant. So what does this mean? This means the points on the sphere in this space. Okay, consider again two-dimensional space. So if we have two dimensions, let's see, this is point C. Then any point x in this set means, so if we take the difference between x and c, so this vector corresponds to this. And take the modulus, which is a constant. So that means wherever this point is, as long as it is in this set S, then the distance between C and X is constant. So that means it's a circle around centered at C. Okay, so this length is R. So wherever X is, this X is, as long as it is in this set S, the distance between X and C is always constant R. So that is a circle in case of two-dimensional space. In case of three-dimensional space, suppose this is C, and then it is a sphere, surface of the sphere. Okay, so it's very hard to visualize. Okay. So if x is somewhere here, c is here, then the distance between x and c is constant r. So this set represents a sphere, the surface of a sphere. And the same is true for higher dimensional space, although we cannot visualize it. But actually, this is the definition of the sphere, surface of a sphere in higher dimensional space. We just used analogy based on two-dimensional space or three-dimensional space. And similarly, so instead of equal, we might define less than or equal to R. In that case, let's call it B. This means inside the sphere, inside or the surface of the sphere. Okay, it's less than or equal to R. So that means in case of two-dimensional space, it is everything inside the sphere, inside the circle centered at C. In case of three-dimensional space, it is inside this sphere, anywhere inside this sphere. So that is less than or equal to R. Okay, and we call this the ball. Okay, centered at C with radius R. Okay, and this set becomes very important when we study higher dimensional integrals.